So in this video, we're going to discuss and define concavity and how to test for concavity. So I have a nice definition here for concavity. I'm not going to read it right now. I'm just going to kind of jump into conceptual identification of what concavity is, and then we'll kind of revisit the definition of concavity. So a function is concave down simply when the function is opening downwards, or visualize it as a bowl opening downwards. So here I have a function f of x shown in green, and through this region right here the function is concave down because as a bowl it is opening downwards, and through here that same function is concave upwards because you can see that it opens like a bowl upwards. So concave down simply means the function's opening downwards. Concave up simply means that the function's opening upwards. So in purple here, I have established some representative tangent line pieces. And what you want to notice is that when a function is opening downwards, the tangent lines to the function are always above the function. And when a function is concave upwards, like it is through here, the tangent lines to the function are always below the function. So that's the first thing to notice. The second thing to notice is about the tangent lines. And remember, when we're talking about the tangent lines for a function, we are talking about the derivative of the function, because the derivative is the function that describes the slopes of the tangent lines to the functions. So here's the next thing to notice that's key or important to realize. So when a function is concave down, what we want to notice is that as we move from left to right on the input axis, that the slopes of the tangent line are changing from positive slopes. So you can see here to the left of this critical point, if I draw in a tangent line anywhere I want, the slope of that tangent line is going to be positive. And here the slope of that tangent line is 0. And then as I sweep through to the other side, now I have lines that are downhill in orientation. So those slopes are negative. So the tangent lines are changing in this concave down region from positive to 0 to negative. This means that the tangent line slopes are decreasing. If you start positive, go to 0, and become negative, you're decreasing in size. So f prime, the derivative, which describes the tangent line slopes, has to be decreasing over the open interval for which the function is concave down, because the tangent line slopes are decreasing, going from positive to 0 to negative. If we look at the open interval over which the function is opening upwards, or concave up, what we want to notice is that the tangent line slopes start negative, then go to 0, then become positive. Here's a tangent line. Its slope is positive because it's oriented uphill. So if the tangent line slopes are going from negative to 0 to positive, and the derivative describes the slope of the tangent lines, then the derivative is increasing. So a quick immediate summary on this is that if the derivative is decreasing, if the tangent line slopes are going from positive to 0 to negative, then the graph is concave down. And if the derivative is increasing, in other words, the derivative or tangent line slopes start negative, go to 0, and become positive, then we have a graph that's concave up. So the first big thing to recognize is that what we need to know to determine whether we're concave down or concave up is just whether the derivative is decreasing or increasing. That's the first thing to know. The second thing to recognize is that there is a spot on the graph at which the derivative changes from decreasing to increasing. So while we were concave down, the derivative's decreasing. While we're concave up, the derivative is increasing. So there has to be a spot on the graph where we change from concave down to concave up, or from a decreasing derivative to an increasing derivative. And that point on the graph where that change happens, that change in concavity happens, is called the inflection point. And the key is that at the inflection point, one of two things is going to happen. Either the derivative is going to change from decreasing to increasing, like it did in this case. It's going to change from decreasing to increasing, or vice versa. It's going to change from increasing to decreasing. One of those things is going to happen as you change from concave up to concave down, or from concave down to concave up. So the inflection point is going to identify the place where the concavity of the graph changes. And so the question is, how do you find that point? So let's talk about this a little bit more. So the next thing that we need to understand is that the second derivative describes the rate of change of the first derivative. So we know if we have a function f of x, we know that f prime, the derivative, is the rate of change of f of x. But the second derivative, what we want to realize is that the second derivative tells us the rate of change of f prime of x. Because the second derivative is the derivative of f prime, it describes the rate of change of the derivative. So now we can think about this a little bit more. If the derivative is decreasing, that means the rate of change of the derivative has to be negative. So f double prime, is the rate of change of the derivative. So if the derivative is decreasing, going from positive to 0 to negative, then the second derivative will need to be negative or less than 0. If the first derivative is increasing, changing from negative to 0 to positive, then the second derivative has to be greater than 0. It has to be positive, because it describes the rate of change of the first derivative. If the first derivative is increasing, its rate of change is positive, so the second derivative is greater than 0. If the first derivative is decreasing, then the second derivative has to be negative, which is what's causing the first derivative to be a decreasing function. And if the derivative is decreasing when we're concave down, and then switches to increasing when we're concave up, then the second derivative is going to need to change from negative to positive. And the only way to change from negative to positive for the second derivative is either for the second derivative to equal 0 or be undefined. So this inflection point on the graph is going to happen one of two ways. This is going to be the place where the second derivative changes from negative to positive, or vice versa. And when it makes that change from negative to positive, the second derivative will either need to be 0 or undefined at that moment of change. So we can kind of summarize this conversation simply this way. We want to be able to test for concavity. And to test for concavity, if the graph is concave down, we want to recognize that the second derivative, which I have right here, the second derivative, when we're concave down, we know that f prime is decreasing, which means that the second derivative, which I actually have graphed here, needs to be negative. So this whole region through which the second derivative is negative corresponds to the derivative decreasing, or a concave down graph. So if the second derivative is negative, I know the graph is concave down. I need to find the place where the concavity changes from down to up, and that's going to happen at the inflection point. So I need to find the inflection points of the graph, And then I want to use the domain of f of x in conjunction with its inflection points to set up test regions. So if the second derivative is negative in a test interval, say from negative infinity up to this point here, if the second derivative is negative in an interval, then the graph is concave down. Notice right here at the inflection point, the second derivative is actually equal to 0. Here's the 0.00 on my second derivative. So we take the second derivative, we set it equal to 0, we find the inflection points, we use the inflection points and the domain of f of x to set up test intervals, and then we check the sign of the second derivative in those test intervals. So here the graph is concave up from this point off to infinity, and what we want to notice is that the second derivative is actually positive. It's above the x-axis. So testing for a concavity. So here's what you need to do to test for concavity. Set the second derivative equal to 0, or find where the second derivative is undefined. That's going to give you the inflection points on the graph. Use the inflection points in conjunction with the domain of f of x to establish test intervals. So for this graph, for example, my test intervals would be from negative infinity to 0, the place where the inflection point starts, and then from 0 to infinity, from the inflection point off to infinity. And I would be using negative infinity to infinity because this is a third degree polynomial. F of x is a third degree polynomial, so its domain is negative infinity to infinity. So use the inflection points in conjunction with the domain to break it into test intervals, and then find any number c inside of the test interval. Plug c into the second derivative. If the second derivative is positive or greater than 0, then you know the graph is concave up. If the second derivative is negative at your test value you pick in the interval, then you know the graph is concave down. So in the subsequent videos that we do, we'll use the concavity test to test for the concavity of a function over open intervals that we find by setting the second derivative equal to 0 or finding when the second derivative is undefined.